So making a database perform at scale, optimizing for billions of rows. This will be a very interesting talk, so I hope you will learn something new, and I hope you will learn something interesting for big data sets and for billions of rows. So I would like to start by saying that we're going to be talking about briefly about a couple of different things. We only have 30 minutes, but I will let you in on a couple of different things during those 30 minutes. So we're going to be talking about a brief introduction, and I will be telling you about why should you care about database performance in the first place. We're going to be talking about what makes databases fast and why, what makes your specific use case be special, and what are you working on, and how to optimize everything in regards to that. And last but not least, we're going to be optimizing for billions of rows, or in other words, the what you need to know part. So before we start, I would like to briefly introduce myself. So I wrote two books, Hacking MySQL and Black Hat Open Source Intelligence. The second book is coming out this or next month. I also founded a data breach search engine at Breach Directory, and I worked at a couple of database companies, worked with a couple of database companies, including several Nines, Archetype, DB Visualizer, Redgate, and other companies. And I also frequently speak at events and organize events as well. So if anyone's around the UK, we're going to be organizing Database Frontiers in October or November there. So everyone's welcome to join. So as far as big data goes, right? So I would start by saying that, you need to understand why you're doing certain things that you're doing in the first place. So most of us first have our own use case, the sort of I want to do something stage. And then when we have our own use case, we say we have a concept, we have something that works, and that we put that concept into an application. We turn that concept into an application. And then once we do, we frequently have problems with the application or with the concept or whatever. And then we do certain things, and then we realize that the problem is the data or the database, and then we come back into our use case once again. And then we try and try and try again. So this is where we face problems some of the times. So high performance behind the back, or what makes queries quick behind the back, is not very hard to understand. So you have SQL queries, you have your database and your server, most likely. Behind the back, they're just simple tasks consisting of smaller tasks, configuration files, or just metals, or just metal, constructions that you have, storage, RAM, and so on and so forth. All of them need to be optimized for your specific use case, but optimizing them isn't as hard as you probably already think about. So why optimize? Well, I read this poll from Peter Zaitsev. This was just a couple days ago from LinkedIn, and it was about how much performance cost do you expect from your database parameter tuning when compared to defaults. Most of the people asked expect around 30%, around a quarter of performance improvement when they optimize their database parameters. And I guess that's reasonable because you cannot really have hundreds of thousands improved query performance if you optimize certain parameters, right? So the problem is that if you have 1 billion rows or more, if you work with any kind of big data set, you will probably start from small things, right? You will probably start from 1 million rows, 100,000 rows, and then you add more and more data. You have 5 million, you have 10 million, 100 million, and then 1 billion. But what most people don't realize is that your problems don't begin when you have a billion or more. They usually begin when you have 2, 3 million or something around that range. So they usually begin in the first stages of your application, of your use case, of your project. So what do you do then? Well, you come back to your use case, right? So if you have 1 billion rows and you, for example, base these all rows on read operations, for read operations, you're mostly running one of the following. You're mostly either running a search engine, either dealing with some kind of logs, activity logs or whatever, either dealing with some IoT data, either dealing with some training data for maybe AI training or machine learning training or whatever. And then you come into theory if you want to optimize your database. right? So theory says that you will evaluate your server and your database, evaluate your stance, then make your database use the a lot of memory, up to 80% for the best results, right? You need to optimize backups, data loading, searching, and deleting, right? And the theory also says that. And you also normalize, index, and partition your database for speed and for performance, right? But in the real world, everything does not quite work the way we expect usually. So in the real world, you quickly realize that inserts, or if you're inserting data into relational databases, inserts, they're not very effective just because they come with a lot of overhead. And if you have a billion rows or more, it's practically impossible to insert them all effectively. So you turn to raw data. You will also realize that even if you have little RAM, supposedly, for example, less than 32 gigabytes is pretty much enough. You can also use hard drives instead of SSD drives or even NVMe drives, because one thing is they're cheaper, and the other thing is if your data doesn't move much, they sometimes have to do the job as well. They sometimes do the job as well. The another thing is that you need to test before deploying, and it's also advisable to use some kind of built-in testing tools to basically see what's the amount of stress testing that your database can take. So there are a couple of best practices for big data. Some of them are related to basics. So for example, overhead, saying that queries are tasks composed of other tasks, and for your query to complete successfully, it has to complete all of those other tasks. And since all of them complete one by one, your queries have to consider a couple of overhead related things. Another thing that you have to think about is most people buy the hardware before they model the data. And if you model the data first and then you choose the hardware second, some of the problems will disappear. And also your specific use case will come with your specific requirements. So it's also very important to realize what you're doing in the first place. So if you're working with read operations in 1 billion rows or more, it usually will go like this. Assuming you're using relational database management systems, you're either going to be inserting things and then dealing with overhead and then dealing with problems because your database will need to start, check for permissions, open tables, and stuff like that. Update on billions of rows will also likely come with problems. It's not impossible to do, but it will be problematic because it needs to consider indexes, partitions, and other things. Select queries will also consider indexes and partitions and other things, but they will make them faster than usual, right? And delete, depending on your specific use case, they may be unnecessary or they may be of little use. Or you can turn to truncate if you need to delete all of the rows in the table. So if you're running a search engine, if you're assuming that you're going to have, let's say, hundreds of millions or even billions of records, you need to come up with some sort of a strategy to do so, right? First, you need to come up with a strategy to import data. And if you import data as is, you're going to be dealing with overhead. So most of us, what we do when we're dealing with bigger data sets, we usually import raw parsed data. And so when we import raw parsed data, your database doesn't have to deal with as much overhead, and your import operations complete usually a lot faster. We search through a subset of data. I'm going to get back to that in a second. We update when necessary. Again, depending on our use case, we delete data when we need, or we don't delete them at all, depending on your use case. Maybe not even applicable. We have to maintain the data. We have to back up the data, right? And when you back up the data, you have to also back up probably raw data sets instead of logical queries because they will have a lot less overhead again to deal with. And then when we back up data, we usually parse the data to basically back up what we need, right? So coming back to speed and coming back to indexing and partitioning and performance, if you ask ChatGPT how to perform performance tuning on billions of rows or even tens of billions of rows, the first thing that it's going to say is if your data is not partitioned, you already lost. And that has some truth to it. So If you partition by range, it helps by narrowing down the amount of rows that your database has to search through. For some search engines, that may not be applicable, but for some other search engines, that will. For example, if you're running a data breach search engine, and if you're searching for accounts, if you're searching for Bob, you can ordinarily just jump into the partition named B and just scan through that simple partition. Right, so it also helps with deleting data, as you can just drop a specific partition or truncate a specific partition instead of dropping or deleting all of the data or all of the tables. And it also helps with search because it speeds all of that up. But again, in the real world, you're probably still going to lose because specific aspects, they are going to make your queries faster, but probably not fast enough for you to roll into production. So if you partition by range, you say to your database that if you have 10 billion records, you search to 100 million. And since 100 million is still quite a lot for your database to deal with, your queries will still complete, but you will likely have not enough speed to deal with again. So the reason why this is because of your architecture, most likely. So you need to have a couple of different things to consider. You need to choose the right database type for your specific use case. MySQL works sometimes depending on what you do. Others turn to MongoDB or other NoSQL database solutions. That's directly dependent on whether your data is in a specific format or not, if it follows a specific format or not, or if it's loose. If it's loose, you're going to use NoSQL. If you parse locally and ingest the data raw, it comes with little overhead. And as I just stated before, loads data in file, for example, will always come with as little overhead as possible compared to insert queries. You need to index properly and partition your data by pattern to make your queries fast, because you need to consider the pattern that your users are using to search for the data before you partition or index. So, and if you do that, you will have better results than if you do otherwise. And sometimes you may need to use specific strategies to plan specific things. So, for example, if you have two columns, but you're uh, inserting data that has 4 or more columns, you can just ignore 2 or more columns and insert data into the only 2 columns that you have. And that comes to schema and data modeling, right? So if you run search operations, you have to consider what it's necessary for in the first place, what you're searching for. Are you searching for cars, for, I don't know, for furniture or for accounts? Maybe you can use limit operations to limit the first accessible row, or maybe first 5 accessible rows, or even if you can use count together with specific database types or whatever, you need to design your schemas backwards, again, for the best modeling experience. So if you have queries and then you design your schemas based on those queries, your schemas will be most likely more effective than if you would do otherwise. You will most likely need to avoid nulls when dealing with billions of rows, because most of the time, they're just a waste of space. And if you don't have a lot of them, you probably won't notice that. But if you have, for example, 100 million or 500 million of null values, they all come with specific bytes that they occupy on your hard drive. And if you have 500 million of such rows, the bytes will add up, and you'll have 12 gigabytes or 15 gigabytes of additional hard drive space that you will need to save. And you need to decide what you're optimizing for before modeling your schemas and data, right? So you can either optimize for read operations, or you can optimize for write operations or other operations. Optimizing for one kind of operation will slow others down. So for example, if you optimize for reads, you will probably have slower writes. If you optimize for writes, you will probably have slower reads and things like that. So strategies to optimize for reads are very simple to begin with. You're just reading too much, too often from the wrong place. And in a way, your database cannot optimize. So what you need to do is you need to partition and index your data effectively. only select what you need. So for example, select column instead of select all. You need to plan for concurrency and long-term strategies. And you probably need to do a bunch of other things dependent on your specific use case. So your specific use case may differ a lot from depending on who's watching this. But in my specific use case, I run a data breach search engine. So if you look at this, you will notice a lot of things that have to do with a specific database, right? So if from the outset, it may not look like this, but if you look closer, you will see that you have specific amounts of records from specific amounts of data breaches. That's one thing. There's the search engine allowed to protect certain kinds of people. That's another thing. That's second thing. When you have a selector that you can select emails, usernames, or IP addresses to search for, that's another thing. When you have the search field, that's yet another thing. When you have specific search fields operators, that's another thing. And when you have a search button, that's yet another thing. And when you have advanced search options, that's also another thing you need to consider. So there are quite a lot of options that you need to consider. So when we take a step back and we say that we have 13 billion rows from the X amount of data breaches, we effectively say that we have the specific number of rows or records in a database. When we say the search engine has helped X amount of people, we say that the number of queries made in total. What's the number of queries made in total? When we select any kind of search selector, so email, username, IP, or whatever, we say to our database that we need to narrow down the search, the part after the where clause, or narrow down the search in the first place. And if you have advanced options, we also have certain things to tell to our database. So when we start digging deeper, we see that behind these things are just simple queries, most often. So the number of rows in a database, what you need to do is you utilize count. The search engine has helped, or the amount of searches that have been performed is just the sum of table rows in total. The part after the where clause is the column that you need to search through. And advanced options, they may differ a lot based on your use case, but they usually have to do something with your database as well, unless you're using an API. So what's behind your specific use case? The number of rows in a database usually means the amount of rows in all of the tables combined in plain English. The search engine has helped means the total amount of searches made, and the plan after the part after the where clause means that you need to index the column or the columns after the where clause, and advanced options are up to you. You need to consider those options because specific use cases require specific different results. But TLDR, to sum it all up, you're going to be fine either way. Just keep in mind your specific use case, your specific server requirements, and your specific project requirements in the first place. You can use hard drives instead of SSDs and or NVMEs. You can use indexing and partitioning at the same time if that's necessary, but obviously that will come with the requisite of space. But you can use even older servers to power applications that have tens of millions of users and beyond. So I hope you learned something from this presentation. I hope it was useful for you. And I hope you learned something new as well. You can find my data breach search engine at breachdirectory.com or learn a little bit more about myself on my personal website. So thank you a lot, and I hope it was interesting to you, and I hope you enjoy the rest of the conference. So thank you.